Today I'd like to show you how we can approximate the square root of 2 using the sexagesimal number system. Now this sounds like sort of a strange thing to do, and basically what we're trying to do is to gain some insight into some of the achievements that took place in calculation ability in Mesopotamia somewhere around 4,000 years ago. So one of the 500,000 or so tablets that we've found that have been preserved through time, because clay as a writing medium can be accidentally preserved when burned, is what looks like a piece of scrap work from a scribe, or maybe a scribe in training, that has a sexagesimal value for the square root of 2 on it. And this value is incredibly precise. It's accurate to something like one place in 10 million. Now, of course, we've got tremendous calculating machines these days, but I want to show you with a transliterated version of sexagesimal just how someone might try and do this sort of thing. And through that, maybe we can, I don't know, gain some muscle memory with hand arithmetic ourselves, if you think that thing might be kind of valuable. And then also gain some appreciation of how good sexagesimal is as a number system, and maybe understand a little bit about how it earned its place as this powerhouse for calculation for millennia, only displaced by decimals with the advent of logarithms, really, so in the 1600s. So without any further ado, let's try and figure out around how big the square root of 2 is. Now the first roadblock here is being willing to admit our ignorance about the square root of 2. Now we're so used to using our calculators and the buttons on them that we tend to identify the square root of 2 with its decimal approximation, 1.414 whatever. But the square root of 2 isn't 1.414 whatever. The square root of 2 is the number that when you square it, you get 2. When you multiply this number by itself, you get 2. And that basic idea is what we're going to be working with when we're looking for a number whose square is 2. When we're looking for the square root of 2. We're going to come up with a guess, and we're going to multiply it by itself and see what we get. The closer we get to 2, the better off we are. Now we can start our guessing without doing anything fancy. And in general, I would recommend having your head on your shoulders, numerically speaking. So this goes along with saying if you're running into a situation where you need pi, just use 3. And if you need more accuracy, then you can spend some time to get more accuracy. In the case of what we're doing right now, before we get into the 1 part in 10 million accuracy, let's get our head on our shoulders in terms of what we're thinking about. The square root of 2 is a number whose square is 2. I know some other numbers and their squares. I know that 1 squared is 1 and 2 squared is 4. So to start with, we know that this number is between 1 and 2. Nothing tricky to that, just a good thing to remember. Again, like I said, to keep our head on our shoulders. So let's try and do a little bit better than that. We don't have to get too tricky. Let's just say it's 1.5. It can be 1.5 written this way. It can be 1.5 written as a common fraction. It can be 1.5 written in sexagesimal. So sexagesimal might be unfamiliar to you still. It probably is. And what I hope is true by the end of this is that that unfamiliarity starts to recede. So what helps me is just thinking in terms of hours, minutes, and seconds. I've got 1 hour and half an hour. Half an hour is 30 minutes. And if I remember that each of these places is half full at 30, is all the way full at 60, then I can actually get pretty far. Something that also helped me when I was starting out is writing this as a geometric series. So this is the 1/60th place, and I have 30 units in that place. And if I have a smaller fraction, it can keep going in that direction too. whatever notation helps you the most. I found that this way of thinking about numbers helped me when I was unfamiliar with sexagesimal, but then as I kept going and I got used to things, I could actually use the places directly, which was kind of nice. Okay, so let's see, how good is it? So along with the guess, we want to check, and by checking, let's call this number here, I don't know if it's a square root of 2, let's call it x, where x marks the spot. Familiar letter from algebra. Anyway, let's check. What I need to do is find x squared. Now, if you've got a calculator handy, you might all be used to squaring that number, or you can get out the standard multiplication algorithm. My belief, personally, is that that's a pain in the butt. With common fractions, squaring is much easier. We can also start getting some practice with sexagesimal. How are we going to square that? Maybe that's hard to see how to square that at first. One way to think about it, though, is this way. And then we FOIL. 1 squared is 1. And then I'm going to get 2 of this middle term. And then I'm going to get this term squared. Now 60 squared, I don't have to compute that. That's in my place value system. This is the next place down. 30 squared, I might need to spend some time with that. But as you'll see, if we look at that number a little bit, it's not so bad. So 2 times 30 is 60. So I've got 60 over 60, so that overflows that place, and it's going to be another unit. And then 30, I can think about 30 as 15 times 2. And why is that helpful? Because 2 times 30 is, again, 60. So this is 1 and 1, and 60 over 60 squared cancels out, and I get 15 over 60. And if I want to write that compactly, oh, whoops, that's 2 and a quarter. Now, as I get used to these places, this might be a little bit easier to do. Maybe I can do this directly by thinking about this as 1 plus 30 in the second place. The notation might be a little strange there, so sometimes it's easier to think in terms of these fractions. But either way, I'd say, I'm obviously most used to this, but I also get pretty lucky here that these numbers turn out nice. And as the calculations get more complicated, I won't have place value to help me out as much. So our guess of 1.5 was pretty close. If you need out in the rest of the world to say what's the square root of 2, you could do worse than starting with 1.5. But let's say we need some more precision. How do we get there? Well, if we're working in the decimal system, we might see if maybe, since this guess was too big, our guess is going to have to get smaller to be better. So what's smaller than 1.5? Well, 1.4. If we're guessing in terms of fractions, maybe we come up with some bigger numbers there. If we're guessing in terms of sexagesimal, here's the part of our number. So if 30 doesn't work, maybe 25 works, maybe 20 works. It's a little bit of a black art deciding what to guess next, and we do it based on some experience with knowing sort of how far we're off. And in the case of both decimals and sexagesimal, as we continue, the place value system will help us refine our guesses. With fractions, we'd ideally, sort of be free to choose any integer possible, and that ends up being kind of too much freedom to make it easy to do good guesses. So let's see what happens as we guess something a little bit closer. I'm going to choose for my next guess 125. and we'll see how that works. We'll look at x squared, which is going to be 1 plus 25 over 60 squared. 2 times 25 is 50. And 25 squared is 625. Now what do I make of this? Well, imagine that I have 600 here. 600 would be 60 times 10. Meaning that I've overflowed this place value and these are actually units over here. Oops, that's weird. And again, I've now overflowed that value. 2, and I'm writing zeros there just to be convenient to notice that this is 2 places down. And for some reason, whatever reason, double zeros feel good to me. We now know that this guess is also too big, because when I square it, I get something bigger than 2. But we're pretty close. This is even close to within 2 places of accuracy. So we know that our accuracy for squaring this number and getting to is already closer than 1 sexagesimal digit, closer than 1 part in 60. And that's about 1.5 digits if we were going to do it in decimals. So this 125 is pretty close. It's probably the closest to sexagesimal digit approximation. But if I want to go deeper, since any further digits I write onto this representation will be bigger than 125, I need to go down to 124 and then add a little bit in the next digit to get that. What it corresponds to is, say, like in decimal, if I found that 1.5 was close, but too big, which we did, then I would guess 1.4 and then start messing around with that third digit there, so that my guess would at least have a chance of being smaller. Our new guess, let's at least check out 124 and check it. Let's see what we get. And maybe now you can see just how much practice we're going to get with our basic arithmetic. And being able to see multiples of 60 within these big fractions, having to carry out some of these multiplications, that's going to give us some good practice. Okay, so 1 and 48 over 60 and 24 squared. Well, I don't know what that is, but I know that it's 4 times 144 because this is 2 times 12. So I've got 2 2s and 2 12s. Maybe that helps. Let's see. And then that's going to be 2 times 2, 88, which is going to be, maybe even just write that in there. And you'll see that there's naturally sort of multiple steps here. How you do multiplication, at least if you want to do it in your head, always depends on the numbers that come up. And you could always kick out to the standard algorithm for multiplication, but I find that this is much less error prone doing it this way and sort of figuring out strategies on the fly to be able to do these multiplications in my head. And this is the kind of thing that people are noticing that looks weird in the Common Core strategies for multiplication. And so while if you just write down one multiplication, it can look like you're going the long way around, the strategies that are taught within Common Core are actually much more useful and flexible in situations should arithmetic come up, although this is pretty contrived. I wouldn't expect this to actually come up a whole lot in real life, and you'll have a calculator there anyway. So big picture, I don't know how much I care what multiplication strategies people like or are attached to, as long as they get the job done at some point. For the purposes of doing this kind of work, it really helps to be able to split these numbers up in ways that are convenient for you. And you don't have to kick out to other places as often to do your work, and you have more direct verification and feeling about the numbers you're working with. Anyway, 2 times 288, I will do something that's a little bit more standard multiplication of this. I'll just do 2 times 8, carry the 1, 2 times 8, carry the 1, and then 2 times 2. So all right, I have 1 and 48 over 60, and 2 times 8 is 6, carry the 1, 2 times 8 is 6, but with the 1 it's 7, and then I carry 1, and 2 times 2 is 4, carry the 1 is 5, 76 over 60 squared. And then I'm going to do something similar before I had more than 600, and so it was more than 10. This is going to be a little bit more than 9 60s. If I know that it's more than 9 60s, I know I'm going to be adding 9 units over here, and so I know that I'm going to not be all that close compared to my previous guess. But that's good because I want to add some more in via the next digit later on. Anyway, this is 540, which is 9 times 60. And then what's left over is 36. All right, and then so all together, I'm going to get 1 and 48 plus 9, which is 57. And then the next place, 36. So maybe with the next calculation, or well, I'll give you a little bit more time to get used to it, but I've found that after doing this enough times, I can keep track of knowing that this is the 60s place and this is the 60 squared place. And so I can do this sort of work without writing out the full fractions anymore. And so it saves some time in writing, but it's a little bit more abstract and you have to have the number system in your head a little bit more. Okay, but so my guess 124 is further away than 125, but I'll be able to add to this to get closer using the next digit, so that I know that the square root of 2 is somewhere between 124 and 125. So let's do that next. Okay, so I know I've got 124 as my first 2 digits. And so for the next one, I know that 125 was a lot closer than 124. So what I'm going to put in this digit will be closer to 60 than to 0. If that makes sense. So my next digit, I'm going to decide how big it is. If I was sort of halfway in between, maybe I would guess 30. But since I'm so close on the other end, I'm going to guess 50. Okay, I now have to check. And this is where things get a little bit more interesting, because now I have to multiply all of that out. And that looks like a bit of a pain. Plus, I'm sort of imagining that I don't have much chance of 50 being right off the bat. I think it's sort of a good guess for what we're going to have, but I'm probably going to have to plug something else in after this, and maybe plug something else in after that. It might take a little while to hone in on what the right digit is, judging by which things are too big, which things are too small, how much they're too big and too small by. And so I'm going to have to do this a lot. And this is a little bit harder than just foiling that simple binomial. It's not terrible, but maybe I could do it ahead of time. Maybe I could say, I know that 1 and 24 are fixed. And then I want to find the number to put up here. So I'm going to maybe do this squaring symbolically first, and then I'll have a formula that I can plug into each time, and maybe that'll save me some trouble. Okay, so if I multiply this all out, I'm going to get 1 and 48 over 60. and that's that squared, and that's this being a middle term times 1. What else am I going to get? I'm going to get this thing times itself, and that'll be over 60 squared. So 24 squared over 60 squared, and I'm leaving some space because I know I'm going to get another 60 squared part when I multiply this by this twice. So this will also be a middle term. And I'm going to get 2a over 60. And then the other term I'm going to get is this one times that one as a middle term. So the denominator there will be 60 cubed. I've got 3 60s, and then I've got 24a, and then I've got 2 of them. So 2 times 24 times a. And I'm leaving that arithmetic undone because depending on what a is, maybe the multiplication is easier one way than the other. And then the final term is this one multiplied by itself. I'm going to get a squared over 60 to the 4th. Now you can see there's a lot more plugging in that I'm going to have to do for now that we're another decimal digit deeper. It gets more than just one part harder because instead of there being 4 terms when you FOIL this out, there are 9 terms. I've collected some of them together so it doesn't look like 9 terms, but there are 9 terms. The next thing to do is to maybe just take a look at this and see where the differences are going to be. This part is never going to change. That one is already fixed. So I can think about starting out with my number as 1 and then 48 and then some other stuff. I also might want to pay attention to which part of this is going to have the bigger effect on the number. So, and I'll just use place value to help my guide. 60 squared is a smaller denominator than 60 cubed. So this is the 60 squareds place, this is the 60 cubes place, this is the 60 to the 4th place. And if I actually wanted to write out literally what this number is, I can write 148 in sexagesimal, 24 squared plus 2a, and then 2 times 24 times a, and then a squared. And notice too that 24 squared is a pretty big number. Maybe I want to take care of some of that ahead of time. 24 squared, we already did, is 576, which gives me another 9 units over here. And then there's 36 left over. So maybe I will start out by writing this as 57, and then 36 plus 2a, and then 2 times 24 times a, and a squared. Now that will do a lot of the work ahead of time for me, so I don't have to do it every single time I plug in a new a. Also, if we're not comfortable with this format yet, we can write our number in that format. So there's 1 and 57 over 60 and 36 plus 2 times a over 60 squared plus 2 times 24 a over 60 cubed and a squared over 60 to the 4th power. It is a big pain to write out all these 60s and it takes more time, but it at least has the benefit of being sort of very obvious if someone else came in and is looking at this number, what's going on. Okay, so that's my general working out what it means to check an x squared that has this 3rd place in it. But now let's check what happens when a actually is 50. Instead of writing all of x squared each time, let's just write out the part that we're going to check and then we'll combine with it. Let's call this the small part. And now say some writing. Okay, so if it's 50, small part, and maybe I can read that just keep that over every time. It's going to be 36 plus 100 over 60, and 2 times 24 times 50. I'll do the 2 times 50 times 24 over, oh whoops, this is over 60 squared, this is over 60 cubed, and a squared is 50 times 50. Hi, sweet. Over 60 to the 4th. All right, so we do still have some work to do here. 136 is 120 plus 16, so there's 2 that comes out. So 2 over 60, and then I'm left with 16 over 60 squared, and then 50 times 24 is 100 times 24 divided by 2, so it's going to be 1200, and 1200 is 20 times 60 over 60 cubed, so I'm going to get some stuff there. And then let's see, 50 squared, that's going to be 2500, which is close to the 2400 I just figured out. So that's going to be, okay, so it's 2500, which is 2400. Let me write this way, which is 40 times 60 plus 100, all over 60 to the 4th. Meaning that I get 2 over 60 plus 16, and then another 20 over 60 squared. You can see this flow of any time you get multiples of 60 in the numerator, it's going to move up to the next place, and you start to get the feeling of how the place value system works. Even though sexagesimal sort of feels strange because there's all these 60s floating around. You start to recognize multiples of 60 in the numerator, and it's not so bad anymore. All right, so that kills out the 60 cubed. It was all coming over here. But then 40 are going to come up over 60 cubed from the 60 to the 4th place. Oh, except there's going to be one more too. So it's going to be 41. And then I'm going to be left with 40 over 60 to the 4th. Okay, now x squared is going to be 157 plus the small part. So 157, I get another 2 places, 159, and then in the x squared place, I'm going to get 36. In the 60 cubed place, I'm going to get 41 and 40. So that's x squared. You'll notice it's closer than our guess for 124 was. That was 157. But there's still some space there. So the question is, could we raise a and still be below 2? But without going a whole lot farther into it, I think it might be just as easy to try something out. I know I could use a practice on my arithmetic anyway. So I'm going to keep track of a few things here. I'm going to keep track of this. I'm going to keep track of this. And then I'm going to maybe choose a equals 51 and see what we get. It's going to be 36 plus 2 times a. A is now 51, so 102 over 60 squared. And you can imagine that I could have been a little bit more efficient and sort of kept most of what I had there. But it starts to get a little convoluted. I'm likely to make mistakes. It's probably just easier to write this out a little bit. All right, 36 plus 102, and then 2 times 24 times 51 over 60 cubed, 51 squared over 60 to the 4th. So this is going to be, again, whoops, let me get my 2 over 60 and have this time 18 left over. Here the multiplication gets trickier, and maybe I will do a little bit of what we did last time. I know what 2 times 24 times 50 is going to end up being, and then so I can just add that extra 1 in later. And then this is going to be 2,500, and then plus 100 for the 2 middle terms of 50, and plus 1 on the end. If you can imagine foiling out 50 plus 1 squared. Two over 60, and then what are we going to get here? We're going to get we got 40 times 60 from that last time. And how do we get that? Because 2 times 24 is 48. Oh, did we do that wrong before? No, that's 48, or that's 2,400, which is 40 times 60. Okay, and then we're going to get another 48. So not a whole other place. 60 cubed, and then so 18 over 60 squared. And then this is 2,400, and so it's 40 times 60. And then there's going to be a 100 from there and a 100 from there. So plus 200 and then 1 over 60 to the 4th. This will give us 3 times 60 and then another 20 for that whole thing. All right, and so altogether I'm going to get 2 over 60 plus 58. 60 squared. And then I'm left with 48. But I'm going to add 43 to it. And then 21 left over. And now here I might start worrying, stuff's going to carry. So 48 and 43 is 91, which is 60 and 31. And so my final small part is going to be, I'm going to get one more unit here. It's going to be 259. I'm going to have 31 left over. And then 21. Okay. And then so I'm going to check, and I'm going to come up here with my small part. X squared equals 157 plus this small part. And if you remember, this is, what place is this? This is the 60th place. So it's that unit, even though I wrote this down without any leading zeros there. And that's in general one of the ways that sexagesimal got by without a zero, is the person who was doing the calculation would sort of keep track of where they were in terms of the places. So that if you're in a situation like this, where you have 1 and then the 60th unit, you're going to add this to it, but I don't want to confuse the 2 here with the 1's place. So that's in my head when I'm not writing it down as complete fractions. But anyway, so it's going to be 1, and then 57 plus 2, which is 59. And then third place is 59, 31, 21. Okay, so I'm getting pretty close now with 51. And since the difference between my guess at 51 and 50 was this unit, the third place, going up by, I don't know, 23, let's say, I can expect that 52 would be too big. So to 3 hexadecimal places, 124, 51 is my approximation. And I'm pretty close. So if I want to go another place, what should I guess here? If I want to change that next place, by half a unit, I think I might start something small. Like my next guess might be 10. But I'm really just pulling that out of thin air. But it seems like a worthy thing trying. You'll also see that the same work that we had to do to create this small part, we'll have to do again starting out with this basis. And even if you're getting pretty tired of the calculations, I think it's at least worth going a little bit further to see that we can do that again and make our lives arithmetically still manageable. So let's see, I'm going to hold on to this, I'm going to hold on to this, and then write out my new guess. Okay, so now what I'm doing is for my new guess is I'm going to add something in this fourth place. So that is 1's place, 60th place, 60 squared's place, 60 cubed place. So I'm going to add some number in that place, some number between 1 and 59. And what I want to know is, again, like I did before, to check, I don't know, I guess if we call this whole number as a whole y. So y squared, if I want to check it, what I need to do is square x plus b over 60 cubed. Which again, just regular old foiling, I'm going to get x squared, and I'm going to get 2 times x times b over 60 cubed, that's the middle term, and then I'm going to get another term that is b squared over 60 to the 6th. So that's a number of places down. You can imagine that b squared isn't going to have a very big impact on what that number ends up being. Most of it is going to come from this part. So we can think about, what do I need b to be to add to x squared? So there's x squared, and I want to add to x squared, and I don't want to get over 2, but I want to get as close as I can by adding something here. So I'm adding something ideally in the third place, right there, the 60 cubed place. And so altogether, I want 2xb to be somewhere around 29, let's say 30, just for right round numbers, because I'm trying to estimate what this effect is going to have. And then the other idea that's happening here, so I want this to give me, this is in the 60 cube place, I want it to give me what's left over there between that and 2. And then I'm also assuming that the effect of this is going to be pretty small, because 60 to the 6 is 2 more places that way. All right, and these are, there's nothing that guarantees these assumptions, but what I'm trying to use them for is to guess what maybe b should be. So if I want to know what 2xb is, then I want to know what 2x is. X is 1 and a little bit. So, maybe like close to 1.5. So 2 times x is going to be around 3, let's say. It's a little bit less than 3. So then 2xb is going to be around 3 times b. And so if I want that to be 30, then I should probably pick b equals 10 as a starting place. So that's what I was guessing before, and now I have maybe a better reason to guess that. I haven't done any of the calculations yet, although I do have my new small part. So this is x squared plus my new small part. And I'll use the same letters there. It's a little bit confusing, but Hopefully not too confusing, not enough to warrant coming up with some new symbol or something. And then what I can do is when I choose b to be 10, or if I end up choosing something else, I can compute this, then I can add it to x squared and see how that turns out. So maybe I could still do this here. Oh, I don't know if I'll run out of room to do the calculations, but let's hope not. So let's try b equals 10. Our small part is going to be 2 times 10 times x over 60 cubed plus 100 over 60 to the 6th. So you can see this gives me 1 unit in the fifth 60 to the 5th place, which isn't a whole lot compared to the effect I'm hoping to have on this number here. All right, so how do I do 20 times x? That's a good question. One way to do it is, all right, there's my x. I'm just going to multiply each place by 20. $20 times 24 is 4,800. And we even found that out before, that relates to 60. Another way to see this is 24 is 8 times 3. So if I pull the 3 over here and make this 60, then I'm going to be left with 8 right there. Oh wait, no, just 8, not 80, just 8. All right, and then 20 times 51, let's see, how do I want to do that? I could just do 10 times 51, which is 510, and then 20 is double that, so 1020. Okay, and then how many 60s do I have hiding in there? Well, let's see, how much would 900 be? 900 would be 600, or 10 60s, plus 5 more 60s to get 300, and then I'd have 120 left over. And that also is 2 more 60s. So 1,000 is, let me write this as 600 plus 300 plus 120. So this is 10, 15, 17 60s. So I'm going to get 17 in the next place over here. I'm going to get these 8 come over here to this place, the 17 come over there. And so be careful though with, I'm doing this sort of amalgamated notation where I'm starting to use just the place value of sexagesimal, but keep in mind that this 2xb is over 60 cubed. So this is really the 60 to the 3rd place. Okay, so the small part altogether, if I want to be careful about my places, is 0 in the 60th place, 0 in the 60 squared place, and then in the 63rd place I get 28. Remember I wanted to get 30, so that doesn't seem too bad. In the 4th place, 17. In the 5th place, I'm going to get 1. And then in the 6th place, I'm going to be left with 40. All right, and then let's check out what x squared is going to be. Maybe I'll still write this up here because then it'll be at the top of the board. So, y squared is going to be x squared plus the small part, which is going to be 159, 59, because small part doesn't have anything in those first places. And then in the 3rd place, I'm going to get 31 plus 28. In the 4th place, I'm going to get 21 and 17. And in the 5th place, I'm going to get 1. And in the 6th place, I'm going to have 40. So altogether, 1, 59, 59, 59, whoa. And then 38, 0, 1, 40. Okay, that's getting pretty close to 2. We are off by less than 1 place in the 1 over 60 cubed place. So how big is 60 cubed? I don't know. What does it correspond to in terms of our decimal system? I don't know that either, but I know we're starting to get pretty good. I don't know if you still have any left in you. Me, I'm starting to feel like there's sort of a flow here. I know that 10 was a good guess. I still ended up under 2, which means I can go to the next digit without having to see what 9 is, because I'm still under 2, so I can still add to this number. This idea of using a binomial by starting with my old guess and adding something in the next place to it, figuring out a little bit of the arithmetic ahead of time, and then just having to find this small part seems like it's something I could keep doing. I guess we could check what happens if b is 11 and see if we still end up under, but since we hit nail on the head at 59 in that place that we're trying to work out, I wouldn't push it. I'm sure b is 10. Because if b being 10 gives you 28 there, another b is going to give you at least 3 or something like that. So let's go another place. What am I going to need to keep? I'm going to need to keep y squared. I'm going to need to keep my new guess. Where did I write that down? I didn't write it down all the way. I'm going to write y equals 1, 24, 51, 10. And then let's see. In this new place, what's my new guess going to be? In the next place over, the 4th place, I've got 38. Well, I can go through this whole business here and maybe get a better guess, but without even doing anything yet. Last time I wanted to make up about 30, and that was b equals 10. If I want to make up around 20, I don't know, like maybe b equals 5 or something like that. Maybe a little bit bigger, maybe a little bit less. It's a little bit hard to sort of guess ahead of time because, as you've seen, like the effect isn't quite simple. But anyway, a small b. I don't have a lot to make up there. All right, so let's see what we get. Z is going to be y, and some of c in the 60 to the 4th place. So I'm going to check it. I'm going to get z squared equals y plus c over 60 to the 4th squared, which is y squared, and 2yc over 60 to the 4th plus c squared over 60 to the 8th. So it's still got to know 2 places back. And we'll put this thing right here, our small part, and so we have 38 in 60 to the 4th place. And we want 59, so we want a total of 21. And I'm imagining that when I start putting in things for c, this is going to be small. C squared over 60 to the 8th is going to be small compared to the 60 to the 4th place I'm trying to work on. So most of it's going to come from here. And then I want 2yc to be that 21. Again, y is around 1.5, making 2y around 3, which means maybe that c should be 7. Does that seem like it makes some kind of sense there? Okay, let's try it out. And then we'll use this calculation to figure out what happens when c actually is 7. Let's see, I'm trying to add y squared in the small part. So I know that these first parts just belong to y squared, and then this is going to be 60 to the 4th. And so I add it to 60 to the 4th. 60 to the 5th. 60 to the 6th. Here it's going to go over 40 and 56. And then 60 to the 7th is 20. And then the small part that's not in 2yc comes from c squared, and the 60 to the 8th place is 49. All right, so let's see, 40 plus 56. So same. 40 plus 56 is 96. which is 60 and 36. So I get one more over here. 49 and then 36, 20, 49. Maybe I should just go ahead and write 7. Okay, so that's pretty close. I almost got to 59 there. The question is, if I made C equal to 8 instead of 7, would I still fit under? It's probably worth trying. C equals 8. Can I take most of this calculation for granted and change it slightly? So 2y times 8 is the same thing as 2y times 7 plus 2y. So if I figure out what 2y is, I can just add that on. For c squared, I'm going to get 64. C squared is going to be 64 over 60 to the 8th. So instead of 49 over there, I'm going to have 4 here, and then I'm going to get 1 more in that last place. So the difference between this number here and with c equals 8 is I need to add the 2y to it, because I just figured out what 2y times 7 is. That's right here. And then c squared's difference from that number right there is this is the only contribution from c squared. And so, okay, so how do I figure out what 2y is? I multiply that by 2. So 2y is going to equal 2, 48, 102, 20. And I have to do a little bit of carrying here, but not a lot. 2, 49, and then 42, 20. Okay, so if I add in 2, 49, 42, 20 to this number, that'll represent what happens when I get c equals 8. Well, I also have to add in that part there. So let's call this z sub 8 to remind us that it's what happens when we plug in c equals 8. So I'm going to start out the same, 59, 59, 59. And then it's only when I get to the 60 to the 4th place that this is going to start having an effect. I'm going to have to add 2, and I'm going to have to hope that the rest doesn't carry over, but I can already see we're in trouble. So if I add 2, I get 59 to this number. And then if I add 49 to 49, that's going to be too much, and this whole thing is going to carry over. On the other hand, sorry, I'm gone below the horizon. So I know that when I add 49 and 49 there, we're going to carry over at the same time, and then that carry is going to come all the way past 2 here. At the same time, I know that that's going to be an even closer approximation for 2. So if I want this 4th place to be my last digit, and I don't mind having an overestimate for the square root of 2, I'm going to go ahead and use c equals 8. So let's see what we actually get for that estimate. And then maybe we can go on with our lives and stop approximating square root of 2 in sexagesimal units. All right, 49 and 49, how much is that? Well, it's almost 50 and 50, which would be 100, 2 less is 98. And then after that, 36 and 42 is 78. And 20 is 40. And then instead of 49 there, I'm going to get 64. And then I really did sort of back myself into a corner here. Maybe I can just do my carrying here. So I'm going to get 4. Carry all the way up, I'm going to get 41. I'm going to get, is that even, yeah, it is at least on the screen. No carrying here, but I am already over, so I have 18. And carry the 1 forward. This is 99. take 60 out of that and have 39. Add 1 here, so I get 0. Carry the 1 here, I get 0. Carry the 1 here, I get 0. Carry the 1 here, I get 0. Carry the 1 there, I get 2. Okay, so I'm going to write this a little bit nicer in just a second. But notice how close that is to 2. And again, my number now, my z, is whatever y is, 1, 24, 51, 10, and then a 9, or an 8 in the next place. Using, 4 sexagesimal places after the 1 to approximate the square root of 2, we get a number that is pretty darn close to the square root of 2. Now, how close is that? Well, the difference between this and 2 is just this part of the number. So, how far back are we going? This is 60, 1 over 60 squared, 1 over 60 cubed, 1 over 60 to the fourth. This is 39. Let's say this is off by less than 40 over 60 to the fifth. How big is that? Well, I have done, I think, probably enough arithmetic for one day, so I'm just going to ask Google how big that is. Actually, wait, before I do that, we can at least do some estimations here. 40 is less than 60, so this is less than 1 over 60 to the fourth. If I just imagine this was 60 here and let it cancel one of those powers. Okay, and now I will use Google to tell me how big 60 to the fourth is. It's a lot. So you know what Google told me? Google told me that 60 to the fourth is equal to 12,960,000. So we are certainly within 1 part in 10 million with our estimate of the square root of 2. Well within that. Now the original estimate that's written on the Babylonian tablet actually stops 1 digit short of where we did. We just kind of got going. But I think by working through how much we had to be able to do to work out these sexagesimal digits and knowing some algebraic tricks or coming up with some algebraic tricks to make that arithmetic a little bit more manageable, I think we can appreciate a number of things from this situation. Certainly one is how advanced the computational techniques were in ancient Mesopotamia, something like 4,000 years ago. How capable the sexagesimal number system is. We even got to see a little bit about how maybe you wouldn't care so much about having a 0, because as long as you can keep track of what place you're at in your head, you can get to the answer you need in the end. One of the pieces of information that was actually missing about the sexagesimal system in what we've read so far is that it wasn't a number system or a system of units that people used when they were counting things every day. It was just an official, scholarly, bureaucratic number system. So you can kind of imagine something like that today, where in the US, we haven't adopted the metric system officially in a lot of places. So we still get things in terms of pounds and inches and feet and everything like that. But if the things that you're buying are actually produced through some sort of industrial economy, if you go to that factory and work with those planners, everything is in terms of millimeters and kilograms. So there's this sort of other number system behind the scenes that people are using when they need the calculations to work out well. And then when it's time to sort of publish results or tell someone how much money they have or how much area is in the rectangle or whatever, the scribes would convert back out to those customary units. And so especially if sexagesimal is just a tool being used for calculation and scratch work, just like we did in our calculations, you can keep track of the places in your head. And many of the other tools that people have come up with over the years, so slide rules work this same way, log tables work the same way, where they expect the person doing the calculation to keep track of the basic places that they're in. And then the tool itself will keep track of all the little vicissitudes that you need to carry out your computations. So anyway, I hope that this question, despite its eventual frustration, has turned out to be one that you found interesting, and I hope you've come to enjoy Sexagesimal a little bit. And talk to you later.